Good morning, students. In the yesterday class we were discussing about the infinite impulse response filter format, where we have seen what is the transfer function of the IR filter in terms of its numerator and denominator coefficients, and then we discussed the bilinear transformation design procedure. What are the steps involved in the bilinear transformation method? That is basically converting the digital frequency, the digital filter specifications into a analog filter specification using a frequency morphing, and then the second step is to design the analog filter using the low pass prototype, and then the analog filter is again converted into digital filter by using various transformation techniques which are available in digital signal processing, like bilinear transformation technique is one of the widely used the transformation technique, and then the backward difference method is there, then impulse invariant method is there, and matched Z transform is there. So these are the four the transformation techniques available to design the digital filters from the given analog filters. The most widely used the transformation techniques for designing a digital filter is the bilinear transformation method. So in the today's class we'll discuss the bilinear transformation method. So bilinear transformation, the first point in this one is the bilinear transformation method is used to transform an analog filter, is used to transform an analog filter to digital filter, analog filter to a digital filter. And this method uses a trapezoidal rule for integrating a continuous time function. And this bilinear transformation uses a substitution S is equal to 2 divided by T into 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1, right? So let us derive how this S is equal to 2 by T 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1 substitution comes. And to derive this one, so let us consider a continuous time function x of t, so which is a continuous time function t. So basically this is like this, right? So now let us sample this one, like this, right? So what is the area under this curve? What is the area if I take these two samples? So here I will take n minus 1 times t, and here it is nt, right? And this sample signal, let me call this as y of n minus 1 t, and this one is y of n times t, where t is known as a sampling interval, right? So in order to derive this substitution for bilinear transformation, so we have to assume x of t be the continuous time function, and when you sample this one, right, so you will get so many number of samples, right? So between any two samples, in order to find the area under this curve between these two samples, right, so by considering capital T as a sampling interval, right? So now, so this is, if I take this point, we will consider it as y of t, right? So now let us take the derivative of this y of t, right? So this derivative, because how to calculate the area? By taking the integration of this one, yes or no? Integration of x of t. So if I take y of t can be computed by taking integrating x of t over 0 to t. Understood? So the same thing can be written as, if I take the differentiation on both sides, so what you will get? D by dt of y of t is equal to, differentiation and integration will get cancelled, so we will get x of t, right? So the area under this curve is calculated by integrating x of t from 0 to t. But in this case, what are the limits? We have the limits from n minus 1 times t2 to n capital T. So lower limit is n minus 1 times t and upper limit is n times capital T. Understood? So if I take the Laplace transform of this one, so what is the Laplace transform of this y of t? Since it is derivative, so what you will get? The Laplace transform of this derivative, you will get s times y of s is equal to, what is the Laplace transform of this x of t? So this is x of s. Understood? So if I write y of s divided by x of s, what you will get? This will give you that 1 by s. So what is this y of s divided by x of s? So this is nothing but some transfer function. So this is nothing but what? A some transfer function. So I can write as a g of s or simply h of s in s domain. So this is a transfer function in s domain. Understood? So now let us apply the actual limits for this both LHS as well as RHS. So what is the lower limit? n minus 1 times t. So I will apply here n minus 1 times t, and here it is n times t, d by dt of y of t is equal to y of t into dt is equal to, again integration from n minus 1 times t to n times t. So here it is x of t into dt. Understood? So here the integration and differentiation will get cancelled. So you will get only y of t you will get. So here y of, so before cancelling you have to apply the limits, right? So upper limit is what? Y of n times t minus y of n minus 1 times t, right? And here it is integration from n minus 1 times t to n times t, x of t into dt. Is that clear? Right? So what is this x of t? So x of t is nothing but, it is the area under the curve, the area under the this shaded portion, right? So it is between the two samples, between n minus 1 times t to nt. So how to calculate this area? So area is nothing but, it is the mean height of this x of t between these two intervals, that is n minus 1 times t2 to nt, right? Mean height is what? Let's say this is x of t, right? So what is this one? So this is x of n minus 1 times t, and what is this one? Mean height is plus x of n times t divided by 2, right? So this is the mean height multiplied by height into width. So height into width is what? This one. So if you take nt minus of minus is plus t, so this one and then this one will get cancelled, so you will get plus t. So the area under this x of t between these two limits is given by, right? So the mean height between these two intervals multiplied by the width, that is capital T. Therefore, so y of nt minus y of n minus 1 times capital T is equal to, so this is nothing but x of n minus 1 times t plus x of n times t divided by 2 into capital T, right? So now here if I take t is the sampling interval is very small. If we assume t is very small, then we can assume n of t is almost equal to what? N, and n minus 1 times t is approximately equal to n minus 1. By using this assumption that t is very small, right? So we can approximate n times t is equal to n, and n minus 1 times t is equal to n minus 1. So by using this condition, so this equation can be written as y of n t is equal to y of n minus y of n minus 1 is equal to, so this is this x of n I will write first, plus x of n minus 1 divided by 2 into capital T, right? So the same equation I will write here, just a second. So what is the LHS? So LHS is y of n minus y of n minus 1 is equal to, what is the RHS? X of n plus x of n minus 1 divided by 2 multiplied with what? Capital T, right? So now since we are using this bilinear transformation to transform the analog filter to digital filter, so ultimately we are trying to derive the substitution, that is S is equal to 2 divided by T, right? 2 divided by T into 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1, right? So now we have to convert this time domain into a z domain by taking the z transform. So what is the z transform of y of n, which is y of z minus z raised to minus 1 y of z is equal to x of z plus z raised to minus 1 x of z divided by 2 multiplied by t. That clear? So collecting y of z term here, 1 minus z raised to minus 1 into y of z. So here it is t divided by 2. So this t I will combine with this 2, and here 1 plus z raised to minus 1 into x of z, right? So again we will write this in the form y of z by x of z, which is equal to, what we will get, t by 2 into 1 plus z raised to minus 1 divided by 1 minus z raised to minus 1 into x of z. Is that clear? So this is nothing but what? The transfer function in z domain, that is h of z is equal to t divided by 2 1 plus z raised to minus 1 divided by 1 minus z raised to minus 1. Understood? So if you see the y of s divided by x of s is equal to what? It is equal to 1 divided by s, right? So this is the transfer function in s domain, and this is the transfer function in z domain, right? So this is the transfer function of analog filter. If you find h of s, it is as good as designing the analog filter, and if you find h of z, it is as good as determining or designing the digital filter, right? So by comparing these two transfer function, right, so I can write 1 by s is equal to t divided by 2 1 plus z raised to minus 1 divided by 1 minus z raised to minus 1. So I can write S is equal to it is 1 over this one. So t by 2 becomes 2 by t, and this is 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1. The same thing can be written as 2 by t, right? So here I will multiply z raised to minus 1. So z raised to, sorry, I will write like this: 1 minus z raised to minus as 1 divided by z, 1 plus 1 divided by z, right? So taking LCM and dividing the denominator z term, so what you will get is S is equal to 2 divided by t into z minus 1 divided by z plus 1. So this is the substitution factor used in bilinear transformation method to design or to transform the analog filter into digital filter, right? Where t is known as the sampling interval, right? So if I take one simple example, right? So they will give the first order, the analog filter, let's say h of s is equal to 10 divided by s plus 10. So this is the, since it is s, right? So obviously this is the analog filter. So to convert this into a digital filter, so design of the digital filter is nothing but you have to get the transfer function in z domain, that is h of z, right? So this h of z can be obtained by substituting s is equal to 2 divided by t z minus 1 divided by z plus 1 in the h of s. So in the h of s you have to substitute s is equal to 2 divided by t z minus 1 divided by z plus 1. Here what is t here? T is some sampling interval which could be 0.1 second or it could be 0.01 second, right? So it should be very small, right? So this is how we derive the substitution factor for bilinear transformation technique, right? So I will recap this one. Right? So what we did is bilinear transformation method is basically used to transform the analog filter into digital filter. By doing the substitution, S is equal to 2 by t 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1, or S is equal to 2 by t z minus 1 divided by z plus 1, that is also correct. Understood? So to derive this substitution, right? So now let us consider a continuous time function x of t which varies continuously with respect to time t. Understood? Then we have to find the area under this curve that is considered as y of t, right? So if I sample this signal over this t, right? So I want to find the area between these two, right? So the area between these two is considered as y of t, right? And that is d by dt y of t is equal to x of t. Understood? And by taking the Laplace transform, you will get s of y of s is equal to x of s, and then you will get y of s divided by x of s is equal to 1 by s. Understood? So now by applying the actual limits, right? So here we have applied the actual limits, and assuming if t is very small, then you can approximate n times t is equal to n, as well as n minus 1 t is equal to n minus 1, right? So you get here, and finally y of n minus y of n minus 1 is equal to, and this area under this x of t, the area under this x of t is given by what? The area is height into width. The height is, it is the mean height between these two samples. So this point it is x of n minus 1 times t, and this is actually this y of n minus t, this is x of n minus 1 times t, and this is x of n t. and between this area is given by what?